Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video, I'm going to teach you how to understand nitrile reactions without having to learn any new mechanisms. Of course, I say that you won't have to learn any new mechanisms, but I say that with the assumption that you already know about carbonyl substitutions and additions and already understand hydrolysis. So if you're not familiar with those reactions, watch these two videos, the Organic Chemistry Reactions, Carbonyl Substitutions and Additions one-slide guide, and the Organic Chemistry Reactions Hydrolysis one-slide guide. And those will get you up to speed on everything you need to know to understand this video. Let's take a quick look at the nitrile functional group, starting with the carbon-nitrogen triple bond. Anytime we see pi bonds, the first thing we should think is that we can probably do an addition reaction. Next, we should probably think that pi electrons are usually involved in resonance, and in this case, of course, that is also true. Next, let's look at the nitrogen. The nitrogen has a lone pair and can be considered a weak nucleophile and base, and we can initiate hydrolysis reactions by attacking an acid with that lone pair. When looking at the nitrile carbon, we should note the similarity of it to electrophilic carbonyl carbons. The carbon is an electrophile due to the electronegativity difference between the nitrogen and the carbon, and the resonance. As such, it is a site of nucleophilic attack in the following reactions: addition, reduction, and hydrolysis. And last, we have the alpha carbon. The alpha carbon is bonded to acidic hydrogens, and it's the site of nitrile anion formation, similar to the enolate with a carbonyl. We won't be focusing on the alpha carbon in this video. Let's move on to understanding the reactions of nitriles. These are actually very simple, because to understand them, we only need to know two things. First, nitriles behave very similarly to carbonyls. And second, carbon-nitrogen double and triple bonds can undergo hydrolysis. Let's take a look at that first bullet point. If we look at a ketone, and we react it with a nucleophile, and then follow it up by quenching it with water, we'll see that in the first step, we attack the electrophilic carbonyl carbon with the nucleophile, and that sends the pi bond up to the oxygen. In the intermediate, the oxygen now has a negative charge, and that attacks the hydrogen of water, giving us an alcohol. That should look very familiar to you, as it's simply the addition mechanism. When we look at a nitrile, we do the exact same thing when we react it with a nucleophile. The nucleophile attacks the electrophilic nitrile carbon, sending one of the pi bonds up to the nitrogen. Then the nitrogen, with its negative charge, attacks water, giving us a double bond NH. You can see that the mechanism for carbonyl addition and nitrile addition are identical. Now, let's review the hydrolysis shortcut for both nitriles and for carbon-nitrogen double bonds. We use the shortcut for reactions involving excess water and an acid or base catalyst. For nitriles, we're pretty much dealing with a CN triple bond, or, after an addition, a CN double bond. And what we do is we cleave all of those carbon-nitrogen double or triple bonds. For however many bonds we cleaved from the carbon bonded to the nitrogen, we're going to add back that number of bonds to oxygen. Since it's going to be either 2 or 3, we're either going to get a carbon-oxygen double bond or a carboxylic acid. If we look at the result of the addition that we just did in the reaction above to the nitrile, we'll see that we ended with a carbon-nitrogen double bond. Of course, that occurs in excess water. So, looking at the reaction on the bottom of the page, all we need to do is cleave that carbon-nitrogen double bond and replace it with 2 bonds to oxygen, in other words, a carbon-oxygen double bond. So we can see here that after a single addition, the imine intermediate, which is the carbon-nitrogen double bond, of course, can undergo hydrolysis. Now that we understand how nitrile reactions work, let's review 4 important reactions of nitriles. The first is when we react a nitrile with H3O+ and water, or OH- and water. Hopefully you recognize this reaction. This is simply just hydrolysis. And what we're going to do is we're going to cleave the entire triple bond between the carbon and the nitrogen. And in both cases, we're going to get back 3 bonds to oxygen. So in the top example, we're going to get a carboxylic acid. And in the bottom example, because we're in a basic solution, we're going to get a carboxylate anion. And once again, this is just hydrolysis. For our next reaction, we have a nitrile reacting with a strong reducing agent, LiAlH4, or lithium aluminum hydride. We're going to use our knowledge of carbonyl chemistry to understand what happens here without having to understand the exact steps in the mechanism. If we happen to have a carbonyl with a good leaving group, then LiAlH4 will reduce it 2 times, first kicking off the leaving group, and then second, reducing the carbon-oxygen double bond to a carbon-oxygen single bond. Here we have a carbon-nitrogen triple bond, so we can reasonably assume that the strong reducing agent will reduce this 2 times in a similar way that we could reduce that carbonyl 2 times. When we do this, we're going to get back a carbon-nitrogen single bond, and of course we're going to add 2 hydrogens to each of those positions. We don't need to draw the hydrogens on the carbon, but the nitrogen, we can show that those 2 hydrogens have been added. Because this is a carbon-nitrogen single bond, we will not do hydrolysis afterwards, because hydrolysis is only done when we have carbon-nitrogen triple bonds or carbon-nitrogen double bonds. For our next reaction of the nitrile, we're treating it with dibol H. And if you remember from carbonyl chemistry, dibol H is a weak reducing agent of esters and will only reduce the ester 1 time. We can reasonably assume that this will also only reduce the nitrile 1 time. So we're going to take this hydride and we're going to attack the electrophilic nitrile carbon. This, of course, will break one of the pi bonds in the CN triple bond, putting a lone pair on the nitrogen. This will, of course, give us a carbon-nitrogen double bond, and when we add water in the next step, it will then undergo hydrolysis, giving us the aldehyde product. Because the reducing agent was weak instead of strong, that's why we end up getting a carbon-nitrogen double bond, which of course is why we can do the hydrolysis. Last, we're going to react our nitrile with either an organolithium or a grignard. Both of these, of course, are organometallics. And with organometallics, they act like carbanions, or strong nucleophiles. So, showing the reaction of the organolithium, the bond between the carbon and the lithium will attack the electrophilic nitrile carbon, sending one of the pi bonds up to the nitrogen. That will, of course, create a new carbon-carbon bond, while also giving us a carbon-nitrogen double bond. So when we add water in the next step, we are going to undergo hydrolysis, giving us the ketone. Once again, this is just an addition reaction, which leaves us with a carbon-nitrogen double bond, which is one of the scenarios that works with hydrolysis. And there you have it, the 4 most important reactions of nitriles. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.